Okay, so I just want to give you an idea as to what we're going to be working towards. I'll share this with the class tomorrow as well. Your test topics for your Chapter 5 tests. There's going to be 2 extended problems. One is going to be kind of like a curve sketching type problem where you have to find relative max, relative min, increase, decrease, point of inflection, concave up, concave down, either involving exponential function or log function or natural log function. Okay. There's also going to be a particle motion problem. Given position function or velocity function, find intervals moving left, right, increasing, decreasing speed, increase, decrease velocity. We'll spend more detailed time with these tomorrow as well. Okay, so those are the extended problems. And then the rest are kind of like the smaller topics that make up the rest of the test. Find derivatives involving expanding log terms. Right, doesn't have to be natural log, could be log base 3 or log base 5, right? Expand all the way out before you find the derivative. We need to be able to find derivatives involving logs and exponentials of base E and also base A. A just means bases other than E. Derivatives involving product, quotient, chain rule, finding tangent line equation, implicit differentiation. So sometimes that may involve log expansion, but it also may involve product and quotient rule. So we've been doing kind of hitting different variations of these problems over the course of these past days. Log differentiation. These are problems that are where there's no logs to begin with, but we introduce logs into the problem to make the problem easier to work through. And then finally, finding derivative of inverse at a point. Okay. So any requests as to problems that you would like to see, or you just want to just see a random assortment of problems? Okay. So if you guys can turn to your packets, I think we have some time to, we're not going to be able to go through some of these reviews in class, so we can do some of this here. If you guys can turn to page, let's see, let me see if I can, here, yeah, let's start with there's a quiz review page here, which we're not having a quiz this year. Page 9 in your this is in your Chapter 5 packet, not in your test packet. So we'll save the test packet for later. So these are all expansion problems, no calculus involved. So let's skip down to number 6. Number 6 says find the derivative of the function below. We do have a rule. Natural log of u becomes u prime over u. But we want to explore expansion before we do anything derivative related, right? We're trying to make life easy on ourselves. If it's a natural log problem, we want to take full advantage of the properties available. So we don't want to jump into the derivative because this is a messy u value, right? We want to split this up. So any ideas as to how we can split this up? If you have need some references, the log properties are sitting above at the top of page 9. Okay. Any suggestions as to how we can split this up? Okay, here's a hint. Natural log of AB can be expanded into natural log of A plus natural log of B. Okay, does that help? What can we do here? Mm-hmm. Mm-hmm.
Would you use 6 times 6?
Yeah, we can do that. Yeah, we can. We know it's going to be natural log of the second term, but we can just go ahead and clean that up as well. Replace that radical with a rational exponent. Okay, what else can we do? Yeah, bring that down, right? There's no calculus involved here. We're just doing expansion here. Okay, so now are we ready? Right, now we have u values that are relatively easy. U prime over u can handle both of them separately. Y prime equals u prime over u becomes 1 over x. Keep the coefficient for the second term. Okay, u prime over u. Over okay, I'm not going to ask you to find common denominator. That is sufficient. Okay, questions so far? Okay, let's go to the back and explore some other types of problems. Let's go to number 8. Are we good on this page? Y equals x cubed natural log of x squared. What could we use to find the derivative of this? Product rule, yep. I mean, we could expand, but it's probably not worth the effort. I mean, this U value is not terrible, so we can just do U. We can just still go directly into product rule. F prime G plus F G prime. And then G prime. What's G prime going to be for natural log of x squared? What's U prime over U? 2x over x squared. Okay, we'll do a little bit of cleanup. We can merge some of these x's together. This is really 2x to the fourth over x squared, and 4x is 2 down here. I can take 2 of them out. I'm left with x squared. Okay, questions so far? All right, let's look at number 9. Number 9, log differentiation. This is where we want to use log properties, but we're introducing it into the problem where there's no logs at all. Okay. But we introduce it so that we can take advantage of all the properties available. So here, it's a pretty messy problem. I mean, we can go through other methods, but log differentiation allows us to take this messy expression and split them up into easier problems. Okay, so take the natural log of both sides. Okay, so we don't want to do derivative, right? We want to take advantage of all the properties here. So basically, keep in mind the way you expand, if there's multiple terms, is whatever's in the numerator is part of a positive natural log expansion. Whatever's in the denominator is going to be a minus natural log expansion. Okay, so it's going to be messy and long, but the derivative will be easy because you just have a bunch of natural log u prime over u's to handle. Yes.
Sorry, why is it x squared instead of x cubed?
Oh, sorry. Yeah, that should be x cubed. Thanks. Okay, everybody okay so far, expansion? Is there anything else that we can do before we do u prime over u's?
Did you write that 2 down?
Yeah, we can bring a bunch of stuff down, right? We can, yeah, let's bring all the exponents down. Yeah. This one, it's up to you. I don't think it's completely necessary, but I mean, you can. So I'll go ahead and do that. Okay, u prime over u. What's going to happen here, though? What's the natural log of y going to turn into? Okay. So the rule that we're applying for all these problems is u prime over u. Okay, so tell me what's the natural log of y going to turn into? Yeah, 1 over y. We also need to include what? Yeah, we just asked for y's derivative, so we need that dy dx. U prime over u for the rest of these terms here, keep the coefficient. 3 times 1 over x. 1/2 times u prime. Okay, it's one big mess here, but all we need to do is to get dy dx by itself. We're going to push the y over to the right side. So we get dy dx equals y times. I'll do a little bit of cleanup along the way. You don't have to. I see the 20 and 2 can be reduced to be a negative 10. And then there's one more substitution that we can make. What can I do with this y? What can I replace this with, though? Can I replace this in terms of x? What's y equal to? How about the original problem? Yeah, we gotta make that substitution. With log differentiation, you're always gonna have y in the end. You gotta find a way to get your x's back, because this is not a normal implicit differentiation problem. We're using implicit to kind of do that work around so that we can do natural log problems. But in the end, it's a function, so we don't need y's in our final derivative. Okay. Hopefully you didn't run out of room, but I just wanted to show all the steps. Okay, any questions there? Log differentiation is just going to be naturally a little messy, but I mean, we have a pretty complicated function, so it's not unexpected that our derivative is going to look a little messy as well. Okay, any questions with that? Okay, look at number 10. Number 10, it says use implicit differentiation. We see y is kind of mixed into the equation, so we know we have to involve implicit. Is there anything that we can do before we jump into our derivative step? What do you guys see? I mean, we can, but I think it's easier if we can do something before we jump into our derivative. Product rule would be derivatives. Is there something that we do before derivatives? Okay, I'm looking at this term right here. What can I do with that natural log of xy? Is there a different way for me to write that? Expand it, right? If we expand it, will make life easier on ourselves, because otherwise we got to do x, y being u prime over u, and that's product and implicit all at the same time. So yeah, it's not every problem that you can expand, but I'm always looking for things that I can do to make my derivative steps easier. Okay, so now we have all these individual terms. We can take the derivative, and then we're going to have dy dx pop up along the way. Okay, one thing at a time here. X becomes this 1, right? Natural log of x becomes 1 over x. Natural log of y becomes, okay, with what? Dy dx, yeah. 2y becomes
Just -2 dy.
good, -2 dy dx. And then finally, x cubed becomes
2x squared.
3x squared. Yeah. So there ends our calculus step. It's a lot less painful if we can go through our expansion step, which we did. So these are all relatively easy rules. So now we just have to rearrange and be able to group the dy dx together so we can factor that out. Okay, divide the parentheses over. Okay, it's a little messy, but it's okay. Here's our derivative. Okay. Number 12, we'll skip 11 here, number 12. This is finding derivative of inverse at a point. Let me kind of review the steps here. Okay. I like to use this chart to kind of help guide my process. So what we're going to do is you're going to be starting at the bottom corner of your chart, and you're going to kind of work your way around. Okay. So in the bottom here, you're going to fill in exactly what you're looking for. I want to find the derivative of inverse at 11. Okay. So from here, we know that 11 is the x value of my inverse function. So I'm just going to, the top level is just going to be my order pairs. Bottom level is going to be my derivative with the prime. Okay, so something to remind ourselves is 11 is the x value of my inverse, but 11 is the what of my function. Okay, if 11 is the x value of my inverse, then 11 is going to be the what of my function. So there's a special relationship between inverse functions, is that the x and y values are what? Are flip-flopped, right? So that's the big thing, right? Inverse function. If I have an inverse function, order pair of 1, 4 on the function, it's going to be 4, 1 on the inverse. So if 11 is the x value of my inverse, then 11 must be the what of my original function? The y value. Okay, does that make sense? Okay, so what that means is over here, I'm going to put that information here. F of some x value equals 11. Okay. So we have to keep reminding ourselves that whatever they give you in the beginning is really the y value of the original function. Okay, even though it's the x of the inverse, what we're working with is going to be the y value. So whatever they give you here, you're always going to have to involve that, slot it in for the f of x, and make sure that you don't put it in for the x. So we have to go through this little puzzle here. We have to figure out what x value will make this a true statement. Okay. A little bit of guess and check here. I'm going to subtract 11 from both sides. And we have to figure out what x value this is. This is not something that we can factor. We have to just do a bit of guess and check. However, we should be able to find it after a few tries. Okay. Start with 0. If it doesn't work, we'll try 1, then -1. If we keep going, we'll try 2 and -2. Okay. Within 4 or 5 tries, we'll be able to get it. Okay. So let's see if 0 works. If I plug 0 in for x, is that going to make this a true statement? No. Okay. How about 1? 2 minus 3 minus 10. Nope. How about -1? -2 plus 3. Right? Not enough, right? How about 2? Okay. 2 times 8 is 16. 16 minus 6 is 10. 10 minus 10 is 0, right? So we have an order pair. So we got to go through that little puzzle to figure out, okay, the order pair that's going to build that, that's going to allow for that relationship is the function has order pair 2, 11, but the inverse function has order pair 11, 2. Okay, so we've established that connection between the function and the inverse. Okay, are we good so far? So now we're going to figure out what the slope of the graph is at 2, and the slope of the graph on the function is going to be related to the slope of the inverse at 11. Okay. Their slopes will be reciprocals of each other. So we have to spend our time to find f prime of 2. Okay. So how can I go through the steps to figure out f prime of 2, the slope of this f graph at 2? Find the what first? Derivative, okay. Enter 2 in for x. Six times 4 is 24. 24 minus 3 is 21. So we know the slope of the f graph at 2 is 21, which means that the slope of the inverse at its corresponding point is going to be what? 1 over 21. So basically, whatever number they give you, just insert it into the y slot so that you can find the x. Once you find the x, find the derivative, find the slope, and then turn around and flip that slope. Okay. Questions there? Okay, let's do a couple more things here. Try number 3. This is on page 11. This is more review. Let's try number 3. Okay, any idea how we can approach this problem? Is there a derivative rule that can handle this setup? Yeah, exponentiating will make it even more complicated, so we don't want to do that. But maybe on the right track. We do have to think about rewriting it, though.
It's like, that's like ln.
Yeah. So this is another log differentiation problem. So there's 2 types of log differentiation. There's one type where you do it because the other method is too complicated or it's too messy. And then you also have another scenario where there's no other option because there's no rule that exists to handle a variable raised to a variable. So yeah, this is a log differentiation. Oh, it's always natural log. Yeah, we always, I mean, we can do logs of other bases, but natural log is just easier, a little cleaner.
Sometimes we have ln, but sometimes.
Well, log base e is same thing as ln, so we can just always write log base e as ln. But if you have like very specific log base a problems, then we just do whatever derivative that is. But in this case, we introduce natural logs to force it to look like a different problem. Okay, take the natural log of both sides. I rewrote that square root as rational exponent. Okay, now that I'm under a natural log expression, what can I do? Yeah,
Move it down.
this whole thing gets moved down. Yeah. Left side is still implicit. The right side, though, what do we have to make sure that we do if we want to find the derivative? How many terms do you see? 2. Product rule. Yeah, you got to remember. If you want to do log differentiation where you're going through this type of method, you got a variable raised to a variable, there's always a product rule that's going to pop up. Okay, left side is 1 over y dy dx. Okay, f prime g plus f g prime. F prime, there's a little bit of chain rule here. Outside's derivative times inside's derivative. G prime 1 over x. Yeah, your log differentiation will just be messy, which is okay. We'll bring the y over to the right side. And then just leave it as one big mess. But remember, we can bring the original problem back into our derivative. I just spent the time to clean this up. All this is connected, so I just made it one fraction. This is connected, I made it one fraction. And then the final step, let's bring the original variable x back. Okay, we're okay? Let's do another one. Yeah, let's do another one of the inverse ones, just so that you guys can have more practice with it, where we have to work our way around that chart. Number 5. So again, keep in mind, whatever they give you, you got to keep reminding yourself that's not the x value, that's really the y value. So don't put it in the wrong slot. Okay. I know 13 is really the y value, so I have to work backwards to figure out what the x value is. We'll put 13 in for y and try to figure out backwards what the x value is going to be. Okay, we go through our numbers to test. 0 doesn't work. 1 doesn't work. -1 doesn't work. How about 2? Eight plus 8, 16, 16 minus 16 is 0. Okay, so it looks like 2 works. So that means if I can find the slope of the f graph at 2, that number is going to lead me directly to the slope that I'm looking for. F prime of x, f prime of 2, three times 4 is 12, plus 8, which is 20. So I know the slope of the f graph at 2 is 20, which means the slope of the inverse at 13 must be what? 1 over 20. All right, so we hit some of the big topics from 5.1 and 5.3. Let's do a couple problems from 5.4, 5.5. So I think the very last page of your packet, there's a 5.4, 5.5 review. Let's just do 2 more problems. Let's do number 2 and let's do number 4. So if you see a log problem that's not natural log, pretend like it's a natural log problem and just work as far as you can go. And then when you're ready for the derivative, you know that there's just that slight adjusting of the derivative rule. Okay, so number 2, big expansion, right? Expand it all the way out like you would if it was a natural log problem. And we'll talk about the derivative after that. Something we got to keep in mind is that as we expand, any term, any coefficient is going to have to be distributed to both terms, right? So that's something just to keep in mind. That, I mean, you can expand with a 3 outside, but ultimately the 3 has to make its way to both of the terms. Okay, is everything nice and easy now for our u value? Your u value doesn't have any messy exponents, right? These are relatively easy derivatives there. So let me write the rule that we're going to apply. Looks a lot like natural log. There's a u prime over u with just a little bit of conversion that has to occur in front. Okay, keep 3, do our conversion, and then u prime over u. Keep 3, conversion, u prime over u. Okay, looks messy, but we can just try to clean up as much as we can here. The 3's can cancel out. A couple of the x's can cancel out. If you're not combining the way I'm combining, that's okay. You don't have to. I just want to clean up as much as I can. Okay, last one here, number 4. Same type of problem, expand all the way out and then apply our log base A rule. You can check the back for the key for number 4. Okay, let's take a look, see how you guys did. So number 4, sorry. Okay. You got the log of A top over bottom, log of numerator minus the log of the denominator. Rewrite that radical as a rational exponent. Push that exponent down. Now you have a relatively easy u prime to deal with. We got to adjust for the fact that it's not log base E, log base A. So A is 5, so 1 over L in the 5, u prime over u, negative 1 over 3 minus x, minus, keep the coefficients, 1 over L in the 5, u prime over u. 1 minus x becomes negative 1 over 1 minus x. Leave that, that's fine, or you can try to do a little bit more cleanup. Okay. Okay, any questions? Okay, so I'll have a help session tomorrow afternoon as well. We'll probably just pick up problems that we don't finish tomorrow in class with test review, okay? And then test review Thursday morning and Friday morning as well.